I am Dixon K. Chembe. Welcome to my channel, and today we're going to look at examples in using node voltage method in circuit analysis. Example 1. So the question says find the values of all node voltages. So solving example 1, we look at the circuit. We've got a voltage source connected to these resistances, and then we have to choose the arbitrary movement of current. Now we know very well that VC is going to be equal to 0, and therefore the potential here is known. What we need to find is the potential at A, the potential at B, and the potential at C. So we follow the steps. This is going to be VA, VB, and VC. And from the circuit, what is known is that VA is a known value. If you remember very well, we've got zero potential here and a voltage source there. This is the first case scenario when we looked at the analysis. Therefore, what you have here is that VA is going to be equal to 10 volts, and this is automatic. So what we need to find is only VB and VC from the circuit. So to find VB, since VA is known, we choose the arbitrary direction of current flow. So we have I1, we've got I2, we have I3, and we have I4. So we begin solving. So for VB, we make KCL at node A. So we apply KCL at node A, which will give us I1 is entering the node, and I2 and I3 are leaving that same node. So if we add the two nodes that are leaving, I2 and I3, it should be able to give us I4, which is the current that is entering that node. And we know from this circuit that our I1, sorry, this must be I1. So we know that from here, our I2 is simply VA minus VC, which is 0 over 10 ohms. So I2 is VB over 10 plus we've got I3, which is VB minus VC, VB minus VC over the resistance, which is 20. This must be able to give us, and mind you, take that in brackets, this must be able to give us our current I1, which is VA. Now we know VA is 10, so it is 10 minus VB over the resistance, which is 20 in this case. So having done that, we could simplify this solution. We know we've got VB here, we've got VB, which is a positive value as well, and then when you take this over the equal sign, that becomes also VB. And if we simplify that, so we have VB 1 over 10 plus 1 over 20, which is this VB, and that crosses over the equal sign. It becomes also a plus 1 over 20, and then we've got minus VC 1 over 20 must be able to give us 10 over 20, which is simply 0.5. So we've got this equation. This portion can be simplified, meaning when you simplify this, you've got simply getting VB. This is multiplied by, so here you've got 4 over 20 minus VC over 20 must be equal to 0.5, and that's what we get. And then from there you can further simplify it by simply multiplying by 20. So we cancel the fractions, we remove the fractions, and what we get here is 4 VB minus VC gives you 10. That is node equation at node B. That is node B. So this equation is done. Okay, now that we have the equation for node B, we go to find the equation for node C. Now, if you look at node C, we've got the current entering, which is I3, and the current leaving, which is I4. So in short, we are saying I3 must be equal to I4, which we can write in other ways as I3 minus I4 equal to 0. Then we expand this. What is I3? I3 is VB minus VC. So VB minus VC over the resistance there, which is 20, minus I4. I4 is VC minus VC minus, we can label this as VD, which is 0. So it's simply VC over 10, and that must give us 0. So from there we expand. We've got VB here, we've got VC and VC over 10. So in short, we can say this is VB over 20. This is minus VC, which both are minuses. So we have 1 over 20 plus 1 over 10. That must give us 0. So when we simplify this, we end up with VB over 20 minus 3 VC over 20, and that gives us 0, which you can simplify further to remove the fractions. You can multiply by 20 to get simply VB minus 3 VC equal to 0, and this is the equation at node C. So we've got node C equation done and completed. These are the two equations that we've obtained. This is at node B and this is at node C. So we solve these equations simultaneously. And what we can do to do that is we can multiply these values by, let's say here by 1, we want to eliminate VB, and this by 4. So when we do that, we get the equation. The first one is maintained, 4VB minus VC equal to 10. And what we have here, so we can have a minus here, minus 4V4, so that we get minus 4VB. This is plus 12VC is equal to 0. So from here, we can see that when we add this cancels out. So we've got 0 here. We've got 11 VC, which gives us 10. And when we get the value for VC, it's supposed to give us 0.909 volts. That's the value of the potential at VC. And then we now use this to put it into the equation. So we can choose one of the equations. We can say 4VC 4VB minus VC equal to 10. We replace in there our VC, which becomes 4VB minus we've got 0.909 equal to 10. From here, VB is going to give us, so 10 adds to that, that's 19, that's 10.909 divided by 4, which gives us VB to be equal to 2.727 volts. So finally, we found our VA is equal to 10 volts, our VB is equal to 2.727 volts, and our VC is 0.909 volts. How can we verify this? We can pick this portion of the circuit and apply KVL. So we know that Kirchhoff's voltage law states that the sum of voltages in a closed loop must be equal to 0. Or so the sum of voltages, the voltage source must be equal to the sum of the voltage drops. So if we pick the voltage drop at the 20 ohm resistor plus the voltage drop at this 10 ohm resistor must be equal. We know this is 10 volts, and we know the voltage across the 10 ohm resistor, which is basically the voltage that we found as VB. So across the 10 ohm resistor is 2.727 volts. But then we have to find the voltage across the 20 ohm resistor, which is between VA and VB, which is basically the potential difference. So we can find it in two ways. We can subtract 2.727 from 10. Well, that is one way, which will give us 7.273. Or we can also get the value of the current. We know the current I1 must be equal to VA minus VB over the resistance. And we know VA is 10 minus VB, which is 2.727 over 20. That gives us the current to be equal to 0.3637 amps. And applying Ohm's law, V is equal to IR, we can then find the voltage across the 20 ohm resistor to be the current, which is that, multiplied by the resistance, which is 20. And when we do that, 0.3637 multiplied by 20, this gives us 7.273 volts. And when we add these two, it gives us 10 equal to 10, which proves that this calculation is correct. Okay, now let's look at example 2. So we've got to find the node voltages here, but you'll notice that the lower voltage, the lower circuit is not ground. So we choose this and ground it, and this obtains a potential of 0 volts. And then we've identified this is node, for instance, A, and this is node B. So this we give it as node C. So VC is equal to 0. Here we have VA and we have VB here. Okay, and so our question is to find the node voltages that are in this circuit. And so what we're going to do in this case, if you remember, there are two scenarios that you can use. One is to convert this into a current source parallel to a resistor, or you can create an imaginary node here. You create the first case scenario, and by creating the first case scenario here, this node, which we can label as D, the voltage across this node VD is simply going to be equal to 10 volts. Okay, so if we have 10 volts there, And then we now choose the current directions arbitrarily. Usually the resistance is connected to ground. We have the current flowing into ground. And then here we have a current that is flowing from voltage source. We know it flows out of the positive terminal. And then we've got a current going in there. So if we label this as I1, I2, I3, I4, and we start looking at node A, for instance. So node A, what we have is we apply KCL, which means the sum of currents entering equal to the sum of currents leaving. So in this case, we've got more currents leaving. So I'll say I2 plus I3 should be able to give us I1. And we know that I2 is simply VA minus VC, which is 0, divided by 5, which is the resistance here. So we've got VA over 5, because VC is 0. That adds to I3, which is VA minus VB over 10 must be equal to, so we look at our node here, which is a imaginary node, which has the potential of 10 volts. So I1 is 10 volts minus VA over 10. So we've got 10 minus VA over 10. And that is the equation that we make on node A. And we simplify the equation further. We obtain, so here you've got, we can say VA over 5 plus here you've got, we can expand this, or the simplest way is to say we've got VA there. So we have VA, open bracket, 1 over 5. We've got VA over 10 here, 1 over 10. This crosses over the equal sign, so it becomes a positive, so 1 over 10. And that, then we've got a minus VB, 1 over 10, equal to 10 over 10. And then when we simplify this further, we obtain, so we've got the common denominator is 10 here. We've got 2 plus 2, which is simply 4 VA over 10, plus we've got, that is a minus VB over 10 equal to 10 over 10, which we can simplify by multiplying by 10 to simply have 4VA minus VB to be equal to 10. And that is the first equation that we obtain. So for node A, this is the equation that we obtain. And now we go ahead to make the equation for node B. So here we've got I3 entering and the 5 amp entering and I4 leaving. So we can say what is entering is, we've got, you can say I3 plus 5 equal to I4. Okay, or we can simply say I4 minus I3 equal to 5. So what is I4? In this case, I4 is simply VB over 20, and this is minus I3 is VA minus VB over 10, and that equals 5. Now you notice that there's a bracket here because this minus and minus have to change variables. So we've got a VB which is common here, VB 1 over 20, and this minus minus gives us a plus, so that is plus 1 over 10. And then we've got a minus VA here, which when you get here, you've got minus VA over 10, plus that must give us 5. And when we expand and also multiply by 20, we simply get minus VA, that is minus 2 VA, plus 3 VB equal to 100. So the two equations that we obtain for node A is as follows, and then for node B, this is the equation that we obtain. So we can solve these two equations simultaneously. We can multiply this by 3 and multiply this by 1. So what we get here is 4 VA minus 3 VB. This should be able to give us 30. And then here we have the same, so minus 2 VA plus 3 VB gives us 100. When we add this, what we obtain is this cancels out. So what we remain with here is 10 VA equals to 130. So then our VA is simply 13 volts. And then we replace this in one of the equations. So we can say for this equation, VA, which is now 13, and we subtract VB from there, must be able to give us 10. So VB, if you calculate here, will give us 42 volts. Finally, we find VA equal to 13 volts, VB is equal to 42 volts. And we end there for today. Thank you for watching. Subscribe to my channel. Good day.